Okay, hello everyone. My name is Miguel. I'm currently working at Google as a staff engineer, focusing on root of trust security. I'm a new face in the Caliptra project. I have felt very welcomed, and I really appreciate the collaboration with our partners, specifically for this particular topic with Microsoft, who has done a lot of the heavy lifting on the hardware integration, and also lowRISC, who has collaborated on some of the IP development. So over the next 12 to 13 minutes, I will go over Caliptra Subsystems Manufacturing and Production Debug flows. We will cover a bit of the lifecycle infrastructure available in Subsystem, as well as the fuse controller infrastructure. And then I will leave a few minutes at the end for Q&A. So let me see. There you go. Okay. So why secure lifecycle management, and why does it matter, right? So let's start with the fundamental problem. For any root of trust, the core challenge is managing the device lifecycle. How do we let factory partners to test the chip? How do we provision secrets? And how do we debug failures in the field? All without creating vulnerabilities or exposing critical assets. The Caliptra approach, which is designed from the ground up, is hardware enforced and state-based model. So basically, we try to rely on hardware as much as possible for guarding assets, critical assets in the system, and creating distinct privileges across different lifecycle stages. What you can do in a trusted factory setting is very different from what you can do in the field. So that we make those distinctions. And so there are a couple of components that enable this infrastructure in Caliptra Subsystem. On one hand, we have the lifecycle controller, which maintains the lifecycle state of the SoC. And the state itself is stored in fuses, so it cannot be tampered with. And the second thing is the fuse controller, which provides a different security features, which we will go over in more detail. So the first thing to go over here is the lifecycle controller. The lifecycle controller is the main interface to it is a tap interface. So that's how we actuate lifecycle transitions. And the lifecycle controller is the heart of the security policy of Caliptra Subsystem. We started with the OpenTitan lifecycle controller as the starting point, and then enhanced it significantly to meet Caliptra's requirements. In the lifecycle controller implements a forward-only transition state machine, meaning that as you go through the manufacturing process and runtime operations and RMA flow, you're only doing so in a forward-only fashion. And at the same time, we also provide additional functionality to implement debug unlock. The state diagram that you see in here is not complete, so there are some state transitions that are not covered here. If you want to get a full detailed view of all the available transitions, please take a look at the Caliptra Subsystem specification. And the other thing to note here is that for the dotted lines in here, we have transitions that are actuated via tokens. So you need to have a token, wield a token, in order to execute the lifecycle transition. The types of tokens are different depending on the lifecycle stage you're in. So if you are in a manufacturing state, the tokens are implemented using symmetric crypto. So we use token hashes to actuate those transitions with the assumption that manufacturing has some level of security into it. And then for production debug unlock transitions, we used asymmetric crypto that is also PQC compliant, and this is also to make sure that we are maintaining the Caliptra security posture. The other big component in the Caliptra subsystem implementation is the fuse controller. You can think of the fuse controller as the vault and as the storage media for the state of the device. In particular, the fuse controller used in Caliptra implements the concept of hardware partitions. And if you look at the table here, the UDS secret and the field entropy partitions, as our example, are hardware partitions. These are special partitions because they enforce isolation from software. So MCU doesn't have access to those partitions. And we also implement additional countermeasures on top of that. We implement scrambling and integrity protection so that we're able to detect any tampering and also defend against optical attacks. And then we also have another class of partitions. We refer to them as software partitions. These are partitions that are accessible to MCU. Some of those partitions are used to implement, for example, OCP functionality. So it's a very extensive architecture. We also provide tooling to integrators so that they can extend the memory map as needed without having to work around the actual implementation and without violating the Caliptra integration specification. This is also a very interesting slide. So for those familiar with Caliptra Core, Caliptra Core has the concept of security states. We have, which are on the right column. And then on the Caliptra subsystem side, we have additional signals that are used to manage the debug functionality across lifecycle states. This table is also available in the Caliptra subsystem specification if you guys are interested to get more details. Let me see. Yeah, so I think that's good for that. Okay, so there are two types of debug unlock functionality available in Caliptra subsystem. We separate them into manufacturing and production debug unlock flows. During manufacturing, we have a special lifecycle state intended for UDS provisioning. So basically, we disable debug functionality in core and MCU so that we can provision UDS secrets in a secure manner without giving attackers the ability to extract those secrets. But at the same time, during manufacturing, we don't want to prevent the entire SoC from being debugged. So we basically use the manufacturing state to lock down the root of trust without locking down the rest of the system, used for the whole purpose of securely provisioning secrets. However, there might be a case where for yield issues or for physical integration issues, we may have to unblock the root of trust for debugging purposes. And for that purpose, we have the manufacturing debug flow. The manufacturing debug flow is expected to run in a trusted factory setting. It unlocks the root of trust without exposing UDS. So any single time we enable debug functionality in the root of trust, we automatically hide the UDS and other assets to make sure we maintain the security posture of the implementation. And the last step here is trust but verify. We basically always required a token and physical presence to actuate the transition into debug enable. And in the case of manufacturing debug, we use a symmetric approach. We use the hash of a token. The asset itself is not compromised in hardware because we only store the result of a hash operation. The operator has to present the token itself to unlock, and this is how we basically harden the implementation. This is I feel like there's a lot of echo. So this is a step-by-step process on how we actuate the debug unlock operation. I think that the main thing to highlight in here is that there is a physical present check, which is actuated by using a strap we call debug intent strap. At the same time, there is a boot FSM break, which is used to put Caliptra core on hold so that it's able to wait for the debug unlock token payload. We always rely on Caliptra core to execute sensitive operations. So in this case, Caliptra core is responsible for setting the debug unlock status enable. All right. And then the production unlock flow is intended to run in an untrusted environment. We only want to allow authorized parties to debug the SoC. And we want to give SoC integrators the ability to define their own policies. So by design, we have support for implementing up to 64 different policies, each one with a different public key used for verification. And the primary concept here is zero trust. So basically, because we want to enforce zero trust constraints, we have to request a challenge from the root of trust, which has to be endorsed by the debug unlock key, as well as the device ID, so that we can bind the payload with a particular device. And similarly, compared to the manufacturing debug unlock flow, we required physical presence. So there is a strap, the same strap we use for manufacturing, we use for production unlock. And then we use a mailbox command to send the payload to Caliptra core and perform the authorization. Something important to note here is that Caliptra core, the debug unlock flow employs PQC crypto, so we support both classic and PQC algorithms in this flow. And the other important thing to note is that policy 0 belongs to Caliptra core and MCU. So if you want to unlock Caliptra core and MCU, you have to define an unlock key and sign a payload with that policy. So I'm not going to go through these because we have a minute left. We have a predefined authorization token format, which is understood by Caliptra core. This goes over some of the fields that I mentioned already. So the unlock level is what we use to bind the authorization payload against the policy. So basically, that becomes a one hot coding index into the public keys that are stored in OTP. And the SoC integrator can use these to define different levels of debug unlock functionality. So you can use them to create your own matrix of SOC debug features and basically bind them to that particular authorization flow. This goes over how we implement the policy in more detail. You can look at the specification for more details. And same thing. Key takes await. I think we talked about this. Two key takeaways I want to mention is debug intent is trap, so physical presence. Anytime there's a debug operation taking place, Caliptra protects itself by wiping out assets, and then zero trust as a principle. And then call to action. Caliptra Subsystems specification is available for feedback. The release is also available. Please provide feedback via GitHub issues or through the project's mailing list, and we hope to hear from you. Thank you. So, I'm not sure if we have time for questions, but yeah.
Yeah, I had one question. So if I understand, for example, if this is used inside a SSD that also uses the OCP lock mechanism for managing encryption keys, when you talk at this level about erasing secrets, that does not imply that you're automatically going to erase any encryption keys over in lock. Is that correct?
That is correct, yeah.
Okay, so it's got to be connected correctly by the integrator at the top level.
Yes, the OCP lock specification has specific flows to actuate zeroization of assets, including those encryption keys. However, when we actuate debug flows, there is you can think of it as a volatile zeroization of critical assets just to protect the confidentiality of those assets when we are in a non-production mode.
Yep. Okay, thank you.
All right, thanks a lot.
Thank you.
Yeah.